hope you guys can hear me. I'm having some technical difficulties. So, close that door. So if I can get some confirmation that anyone can see and or hear me, that would be useful. Oh, nobody's watching yet, so give me a minute.
All right.
Excuse me as I kind of change what's going on here. That'll hopefully be good enough for now. Hi, Mariangeli and Miller and Dennis. Dennis, I already showed you the hydroboration mechanism in class. What part of it do you need me to repeat? Because it's going to be exactly the same on here as it was in class. I only ask because that one will take about 15 minutes to draw out just like it did in class. So it takes a while. There we go. Landcorp. Did we get another pervert bot? Report. It's the second time that's happened. Okay, so is there an answer key to the practice test? No, Kenny, I don't post answer keys. You're supposed to come and talk to me if you're having trouble with them, but you would have to do that before now. So so Dennis, are you talking about with an alkene or an alkyne? Because if you're doing it with an alkene, you get an alcohol. Okay. I was going to say, with when you get an alcohol and the other, you don't get an alcohol, you get the... Mariangeli, you could, if you can draw them, you should be able to explain them. I'll just throw that out there, but usually I just accept it if you can draw examples. Okay, so Dennis wanted to know what that looks like, so, okay. Actually, you know what? I'm going to do it this way. Where's my paint? Nope, that's not my paint. That's my paint. Okay. Because I'm sorry this is all kind of funky tonight. Let me read it this way. That should hopefully be a little bit better. Okay. So, hydroboration, and the reason I wanted to do it this way is so that you can get a better idea. Usually, with this one in particular, if you're having trouble seeing it, it's better to actually write out all the carbons and everything. So, let's say I have my generic R group attached to some sort of, oops, alkene. And I'll just make this a terminal alkene there at the end. Okay. Now when you do the hydroboration reaction, let me change my color. And you can look up some references and some resources that will show you how this forms a complex with the tetrahydrofuran that's used as a solvent. But you can also find references for doing it how I've shown you guys in class. And the way we've been doing it is the double bond attacks the boron, which is an electrophile because it has this open shell here where there's no electrons. And then one of these hydrogens, and it's actually a hydride, okay, so it's like the whole thing, the hydrogen plus those two electrons that are in that bond are going to go on the inside and attack that inside carbon, okay? And so if you do that, a total of 3 times, you end up with something that looks like this. You have a bunch of carbons attached to this boron, and I'm just going to leave those as R groups to condense how much we're having to draw, basically. Okay, so what I want to do is stop right now and ask if everybody that's staring at what I just put up there, if that's making sense to everyone, or if I need to explain something else. I'm just, because this one's hard, so I'm going to take it each step at a time. So, Dennis, Marangeli, Kenny, Miller, whoever's staring, did that make sense? I'm getting confirmation from Miller. Dennis, you're the one that asked the question. You still out there, buddy? Stacy's with us. Okay. Okay. All right. I'm just checking. Just checking. All right. So far, oh goodness, come on. There we go. So far, what we have is a situation where we have this organoborate type thing. Okay, meaning this organic molecule with a boron and everything. And it's going to do weird chemistry because boron's weird, right? I keep kind of reiterating that point. So what I'm going to do is, oh shoot, just kind of redraw this so we can use this as a different starting point, sort of, okay? if you notice, the way that I'm color coding this is actually indicative of where the electrons started. So if you're watching this after the fact, right, the electrons on this hydrogen there are red because they came from the original boron hydride molecule, borohydride. Okay. So now we have the situation where we have 3 R groups attached to a boron that still has an open shell. Okay, there's still an open shell on that boron as it currently exists, which means it's a decent electrophile. Things can attack it that are nucleophiles, things with extra electrons. So what you would do is in basically another beaker, a separate beaker, you would put in hydroxide and peroxide and end up getting this. You've seen this, and then you dump that into the reaction. Some people were like, well, why would that attack this and that attack that, and, you know, all these things. And I was having to explain that that's why it's got like the number 1 and then a number 2, is it's actually like a different separate part of a reaction. So you add them in separately, just if anybody's been wondering about the logistics of that. But so now what you end up with, oops, sorry. Is that, right? And that can attack the boron because HO2 minus is a good nucleophile, okay? Oops. So now you're in this situation, right? Well, we have conservation of charge, and I have negative on one side and neutral on the other, means we're missing a negative charge. So to indicate that it's the boron, I'm going to put that in red. Okay, so now that boron isn't really stable. It's got a valence of 3, but now the valence is 4, so it has a negative charge on it, right? Even though it has a full octet. So it's going to start rearranging and moving stuff around. All right, that's exactly what's going to happen here. So we know, let me see if I can explain it this way. No, I'm just going to show it as a picture and then see if it makes sense. So the electrons here, that carbon-boron bond, it's not a super strong bond. It wants to break because that boron's real funky, okay? If you can just think of boron as being weird and fluorine as being weird, you've gotten like 10% of the class down. So what happens is these the electrons in that bond are going to break. So if you have a model kit with you, you can physically pull apart the carbon to boron and put the bond electrons on the carbon. And so that bond's going to break by running into and attacking the oxygen. That's supposed to look like an arrow. Let me try that again. There we go. Okay. Now, the thing is that that oxygen can kick off. There we go. Okay. So you're essentially having an OH, what's called a leaving group, because it's the thing that leaves. Okay. And then what you get as your product of this, and remember it happens 3 times, is I still have my R and my carbon and a hydrogen and my carbon with 2 hydrogens and the carbon that had a hydrogen from before But now instead of having this carbon-boron bond, this carbon is now bound to oxygen. And it's bound using those original electrons that were on that carbon. Sorry, I think I just covered up my webcam. Oops. And what I want you to notice is what actually changes on the oxygen. And I'll put this in purple. So this leaves. This stays. So literally, that oxygen-boron bond hasn't gone anywhere, right? A way that a lot of people like to do these reactions is they'll basically like make a list of what's still bound, like carbon is still bound to carbon, still bound to boron, right, that kind of thing. Well, in this case, that boron is still attached to that oxygen. So I have to show that. Oops. Okay. So now we've done that 3 times and we get this kind of weird looking molecule where there's no more alkenes. Everything is this weird mix of like alcohols that are attached to a boron. Okay, so at this point I'm going to stop again and say, is everybody with me so far? Are there any questions? Excuse me as I eat a jackfruit. Dennis. Okay, everybody else still good. Okay. Take a sip of tea and keep going then. Oh, actually, let me copy this. I think it will. I'm not good with paint, sorry. Okay. So the next thing, and this is a stable enough product. This is like perfectly fine. But at this point, again, the boron doesn't really do well with other things. I mean, like basically everything always wants to leave boron is what I like to say. So some things that we have available in the solution, right? We have the THF, which is a solvent, tetrahydrofuran. That is important in making kind of the complex with the BH3 that originally reacts. And we haven't really shown that for anything, and I'm going to continue not showing it for anything. I still have peroxide, likely in the solution. I have the deprotonated or the conjugate base of the peroxide. I have hydroxide. And if you have hydroxide, you also have water, generally, because you usually have to dissolve hydroxide in water. Okay? It's generally is an aqueous type of thing. All right? So, of those, the 2 that are going to be the most important are the water and the hydroxide. And I think that that probably inherently makes sense because we know that hydroxide is fairly reactive with things. So, let's say I have hydroxide. Hydroxide is a nucleophile. we have an electrophile because the boron is currently in the status of only having 3 bonds to it. Okay, so again, that open shell is going to be able to receive electrons from a nucleophile, in this case hydroxide. Okay. Now, what that's going to do is it's going to allow that boron-oxygen bond to break. And so we can just go ahead and show that happening right there. I've got boron. This is going to happen 3 times like we've shown before. That boron is now going to have 3 OHs attached to it because that has the ability to happen 3 times. Okay. But now I've got this situation here where it's like, what do I do with that? Well, it's going to pick up a proton from the solution. You do have water in there. You have peroxide in there, hydrogen peroxide. So you do have a proton source, and most places show this happening with water. Okay, so that can pick up water, or pick up the protons from water, giving you your product. So that's about as nitty and gritty with the details as I can get, especially through this platform. It would be easier if I brought a model kit with me, but I never think to do that. And also it would take a really long time to make it go together. But I'm hoping that kind of makes sense. Again, I'm color coding it in a way that you can actually see where everything came from. Which electrons come from what. So hopefully that makes sense. And I can answer other questions if there are any others. So Dennis is telling me that clears it up a lot better. Is it just because I drew it with the carbons and the hydrogens and went really slow? Sometimes it's just an issue of going slow enough that like your brain catches all of it. I mean, literally this is exactly the same way I described it in class. So, you know, if you're like, wow, that made so much more sense this time, sometimes it helps to hear it twice, and sometimes it helps to just hear it really slowly, and like color-coded with all the pictures and stuff, so. So, next question. Don't know if you guys have ever seen the seeds of a jackfruit. They're gigantic. You don't ever have to show sodium and water intermediates for me. A valid question would be, you know, I could give you something simple, like with the hydroboration reaction that we just did, for example. Showing everything as a balanced equation at every step would become quite cumbersome, and I think that's why most organic chemists don't really do it. And there's definitely some that do, and they really like having... Are you okay, Onyx? She's like upside down, rooting around on the bed, snorting at me. Sorry if you're hearing my dog spazzing in the background. But anyway, you don't have to show those for me. A valid question, you know, would be like if you had something really simple, like a simple acid-base reaction or something to balance it and that kind of thing. I don't have a history of asking that question, but I mean, you should be able to do that. Seriously? But anyway, you don't have to show that for me. I went to the Asian market and got jackfruit. I don't know if y'all like that. It's delicious. You're welcome, my dear. Next question. You guys want to practice some nomenclature ones? Oh, hi, Randy. How do I know when a reagent will form a cyclo something? I'm not sure I understand your question. Do you have an example, maybe? I kind of don't feel like we've seen any things forming a cyclic compound, have we? That didn't start off as one? Randy, see if you can get me something kind of specific on what you're talking about. I'll put some nomenclature problems up for people to start working. If you're looking at this and it looks like it's a different chemical drawing program than what you're used to, this one's actually ChemDraw. This one is quite expensive, and so there's only 2 professors on campus that have it, Dr. Matthews and myself, and that's just because of the cost associated. Each license is about $1,000. So if you're like, I don't understand, that looks different than what I'm used to seeing, it's actually a different program. You'll notice a difference between ChemDraw and ChemSketch, and you'll see this on the exams too, is that ChemSketch will always put, they'll end every structure with CH3 groups. ChemDraw doesn't inherently do that. And so if you see both in my stuff, that's kind of the reason why. Okay, let's start those 3. Go ahead and work on those a little bit. Now you guys might notice that when we're doing a lot of these problems, I tend to go in the direction of structure to name and not name to structure. And that's generally speaking just because more people have trouble with this. And if you can do this one, the harder one, you can go backwards. But if you need some help with those two, let me know and I can come up with some names for you. Oh, Randy, I was just thinking, are you talking about, okay, carbene? Because if it reacts with a carbene, it's going to form the cyclopropane. It would otherwise give you not enough electrons. You'd end up with a carbocation, and it would react anyway. So if you've ever used it for that capacity, that's what's going to happen 100% of the time. The same way with the halogenation reaction mechanisms, those are always going to form the polonium ion intermediate, which is a 3-membered ring with a positive charge on the halogen. The same way with the oxymercuration reactions, those will always form the triangular intermediate with the mercury in there. And there's not any exceptions to those that we're going to see. So if that's what you saw in class, that's what you need to be kind of expecting. Does that make sense? There are other reactions that we'll see in Organic 2 that will have some other options. Because as the semester goes on, right, we get more complicated ones. But as of right now, it's just like that. You're not expecting anything else to happen. I hope that makes sense. Let me know if that makes sense. All right. So let me do it this way. That keep showing up that way. Sorry, I'm having issues again. Okay. So I just wanted us to look at this and kind of come up with some naming stuff for it. So what would be my parent chain on this molecule? I don't have my chat box up, so I'm just going to give you a couple seconds to kind of respond either on paper or in the chat box or in your brain. If you're looking at that molecule and saying, I see 5 carbons in a chain, then you were correct. Starting with the aldehyde on the right, and then that CH3 at the left, that would be 5 carbons in a chain. So we're looking at some sort of pentane. At carbon 1, we have an aldehyde, and we have, so let me write this down. Okay, so those are basically the different, you want to sit down now? Thank you. Those are the different components that we... Thank you. Brandon came to get rid of that out of the room, so now I don't have to keep hearing these stupid paws clicking on the stupid floor. Okay, so we have a pentane, an aldehyde, an alcohol, a halogen, specifically a bromine, and we kind of have to put all those together. Well, if you notice, we have an aldehyde and an alcohol, which can go either as a prefix or a suffix depending on which one has the highest priority. So if you remember the priority rules, it was carboxylic acids on top, followed by aldehydes, then ketones, then alcohols. So aldehydes have the highest priority. And so from there, we just kind of have to put things together. So if an alcohol does not have priority, we don't name it with an OL at the end. We name it as a hydroxy something. The halogens, regardless of which ones they are, they're going to go at the front of the name always. And so we basically just have to put that together. I'm going to look There's no stereochemistry that I need to be concerned with here. There are 2 chiral carbons, but the stereochemistry is not indicated, therefore we don't have to show it, right? Okay, so what I need to do is go through here and number my carbon chain. So the carbon with the aldehyde is number 1. The one there at the end is number 5. And so I can put these things together. So bromo comes alphabetically before hydroxy. So I have to put that one first. So that would be 2-bromo for hydroxy. Oh. Sorry about that. And then pent and al. Oops. So I'll give you a second to kind of stare at that and see if you have any questions about it. There we go. And if you do have questions, you can ask me, and if not, I will get ready to do the other one by copying and pasting it from ChemDraw. If it were a ketone and not an aldehyde, would it be pent-1-one? No, because you can't have a ketone on carbon 1. It would automatically be an aldehyde. If it was a ketone on carbon 2, it would be pent-2-one. All right. So next problem. Let me pull up my chat box, see if there are any questions. Okay, looks like we're good. So in this case, my parent chain is a cyclohexene, or if you want to, we can just call cyclohexene for now. I need to think about numbering this. We have an alcohol. We have an amine, and we have an alkene. So those are all the components that we have for this molecule that we essentially need to put together. Again, on the priority list, alcohols have a higher priority over amines. And so we're going to have to name it in accordance with that. So I need to number it in a way. Before we said we just need to number it so everything has the lowest possible number, right? But now we know we need to number it, because in this case, right, you could number it either way, and the numbers would be 1, 1, and 2, or 1, 1, and 2. So we need to number it so the highest priority group has the lowest possible number assigned to it, which would put the hydroxyl group at carbon 1 and the amine at carbon 2, going around in a clockwise manner around the cyclohexane. So that means I'm going to start off with my 2-amino. If an amine does not have priority, it goes in the front and it's amino, not amine. Okay, so it's just a very slight difference in how we name amines, whether they are priority or not. It's literally only 1 letter difference. I have cyclohex, and I need to put 1-ene, right? And then we name alcohols by taking the E off the end. And that doesn't change whether or not you're talking about a cyclic structure or not. Now, and this would be easier if you have a model kit like sitting around you. We don't put in stereochemistry with alkenes that are in rings like this, because there's only one type of conformation it can adopt because of the ring. It can't be like that and be in a ring. Okay, so if you're noticing that we're not putting any stereochemistry on things like that, that's the reason. I hope that makes sense. If you tried to make a ring with that, you wouldn't be able to unless it was a very, very large ring, similar to the alkynes that we've talked about in class a couple of times. How are you guys doing on these names? Give me some feedback. Alyssa's here. Hi, Alyssa. All right. So the last one I have up there, and we can do a couple more, but just of the 3 that I'd put up there originally. So, I'll make sure I didn't change anything. Hi. Nice to see you. Or talk to you. I can't see you guys at all. So this one here is a little bit different in the way that I have it drawn, so it might be a little bit trickier. I want us to go through and let's just number this. So if I have some kind of awareness, if I'm looking at this and I'm looking at different functional groups, that is a carboxylic acid, that is a halide, specifically a chloro group, and that is an alkene. Okay. Now that alkene, and let me erase those and divide it in half like that. If we divide it in half, I'm hoping you notice that there's no stereochemistry on that molecule. So this group here and that group there are exactly the same. So if we flipped them, right? If you flip 2 groups, if it's different, there's stereochemistry, and if it's the same, there's not, okay? So we've mostly seen that in terms of hydrogens being at the end of something, but in this case I put methyl groups there, and so those would be the same, so there's no stereochemistry. Okay, so that means we need to number the chain, longest possible chain, right? And we want the highest priority group, in this case the carboxylic acid, it's the very top of our list. We want that to be number 1, 2, 3, and it doesn't matter if I pick the carbon on top or the carbon on the bottom to be number 4, it would be the same thing. Okay, so I've got 1, 2, 3, and 4. Okay, so that means that we're looking at a butane here of some sort. I have a carboxylic acid. I don't have really any other functional groups that I would put at the suffix of the molecule anyway, so we don't really have to use any of like the kind of the newer rules that we've learned. I have a 2-chloro group, and then the alkene is also on carbon 2. So that together as a name. I have 2-chloro, bute, 2-ene, right? But just like we did with the alcohol on the previous problem, you take off the ene and you add oic acid, and we don't have to put a number there because carboxylic acids are always going to be on carbon 1. Okay. So I can do some more nomenclature problems if you want. I've got about another 15 minutes, so if you have some more questions, I can answer those if you have them about reactions or what Markovnikov means, or what naming something with an alkene and an alkyne, or anything like that. Feel free to pop in and ask. Oh, you are right, Alyssa. I totally left that part off. Thanks, guys. Let me fix it. How embarrassing. That means that meme is wrong. There we go. I'm going to just cover up my mistake. Whoop. It happens. No, you totally named methyl groups, but I'm not a perfect person, so. Maybe I need to have the guys. I hate to be the one to tell you this, but you have an imperfect professor. The good news is that none of your professors are perfect, but at least this one admits to making mistakes periodically. I try to make as few as possible, but it does happen, so. I know, oh no, I'm shocked. I definitely had a couple professors when I was a student who, like, they were never wrong. They were totally wrong and just refused to admit it. And I was like, I'm not going to be that professor. So if it makes you feel like you have no faith in my abilities, I'm really sorry, but I just try to be honest with you guys. Also, while you guys are here, I got new artwork for my walls. Completely unrelated to chemistry, but I'm really excited about it. And since nobody's asked me another question yet, I'll just tell you. I found lace doilies and I framed them with Goodwill frames. I like it. I kind of had an old 1950s bedroom, so. Oh, hi, Stacy. How do you determine whether Yep, that's it. So, Stacy, if you have Markovnikov, if you are doing an electrophilic addition reaction, right, it will follow Markovnikov's rule unless it's the hydroboration reaction, which is an anti-Markovnikov type of reaction. And that is quite literally the only anti-Markovnikov addition you will learn in your entirety as an undergraduate. So, that's the only one. You only need to know the one. Yeah. So, remember, and this is in your notes, look for something in your notes that looks something like this. Okay, where we talked about stability of carbocations. The whole point of me telling you about that is to be able to apply Markovnikov's rule, okay? So, actually, you know what? I'm just going to keep these here and make a couple alterations to the structures. That is not a good angle at all. So, let's just start putting some carbocations around here on this guy. There's one. We'll act like there's one there. One there. One there. Just kind of plopping some on. We have so many carbocations, but this is just, for the record, these molecules would not exist, okay? But for the sake of conversation, that's kind of what I'm talking about here. Just being able to recognize. Okay, so let's look at these. Notice I do have, oh, I don't have a way to like highlight that, do I? Can I put a carbon there? Okay, that carbon that I just typed in there cannot have a positive charge. It cannot be a carbocation because it is a quaternary carbon, meaning it is a carbon bound to 4 other carbons. Quat means 4, okay? Tertiary is a carbon bound to 3 other carbons. Do I have those on this molecule? Absolutely. One of them is a carbocation, and it's the one right there that I just added on, okay? There's another tertiary carbocation, or carbon right there, but I did not make it as a carbocation. But basically, if you're adding things, whichever one's going to give you the most stable carbocation is the one that's going to be favored as an intermediate. Because remember, we always go towards stability, always. That's kind of the whole thermodynamics thing, right? So there are some situations next semester. I won't even get into that. I'm not going to talk about it right now. You'll see some examples later on where you have to also factor in kinetics is what I'll tell you. But for right now, just always think of things, what's going to be the most stable carbocation. It's going to be the one that has the most substitutions around the carbon. Now, in some cases, if you have, let's say, a molecule that looks like this. Okay, it's not symmetric. And so if you were doing an addition reaction to this, an electrophilic addition reaction, which one would most likely form the carbocation, right? So you basically have 2 options. Where one would form on that middle carbon, which these molecules are upside down from the one I originally drew, and one would be at the outside. So then the question is, well, they're both secondary carbons at that point. You'd likely get some level of mixture of products because they would both have similar stabilities. The one on the left here would be the most stable because it has kind of the most, kind of like thinking like inductive effects, it has the most influence because it's got bigger stuff on either side of it. But I try not to give you guys those problems, and if I accidentally do, I always accept both answers for full credit. So hopefully that makes sense. Let me go back at my checkbox. Okay, how do I know if an alkyne reacts to form an alkene or if it reacts multiple times to form an alkane? Well, it depends on which reaction you're doing and how many equivalents of chemicals you've added. So for example, if you're doing like a hydrohalogenation, if you add 1 equivalent, it'll only take it down 1 step. If you add 2 equivalents, it'll take it down both steps down to the alkane. If you are doing a hydrogenation reaction, right? If you have, in that case, and I explained why, because of the whole working with gases thing, it's very hard to do like 1 equivalent of H2 gas or something, and that's why we have those poison catalysts. So if you have poison catalysts, they will only react with the alkyne and going down to the alkene. Okay? Kenny, working on a problem on one of the old tests, which has an alkyne with a methyl group on either end in a reaction with water. What is the mechanism? Well, you tell me. That's a hydration reaction. In fact, that's almost the exact same one I think I gave you guys in class in your notes. So you should have that one in there. You're talking about doing a hydration reaction on an alkyne, so you should end up with some sort of carbonyl product, either an aldehyde or a ketone, depending on where the alkyne is. Miller asks, do we use the incomplete equilibrium arrows at the end of hydration mechanisms? I like it that you do, if you do. You basically are always going to push the equilibrium towards the keto product. some of these chemical drawing programs aren't real easy at doing that type of arrow. So if you see it typed out, you might not always see it that way. But when we can draw it with our hands, that's really the best way to go, because it's more indicative of what's actually happening. I hope, Randy and Kenny, I hope I answered your question without drawing anything. Let me know if I did not. In the interim, I'm going to give you guys a hard one. There we go. Name that molecule. Fix my bond angle on that one. Kenny, that one has the same reaction mechanism. It was the very first hydration we learned with the alkenes. It's the same exact thing, except the product is the tautomer that converts it to the ketone. So think of that. All right. So I have a rather long molecule here, one with a lot of different types of functional groups on it. If you wanted to, you could name this, and I think you guys can. I'm going to go ahead and work through it with you. So when I look at this, I automatically see, and I'm just going to circle this real fast. Oh, maybe I'm not going to circle it really fast. Let me try it again. I see that that would be my parent chain because it's the longest chain of carbons on the molecule. So on that chain, I have to think about what my highest priority functional group is because it needs to have the lowest number. So I have an alkene, an alkyne, two alkenes, an isopropyl group, a hydroxyl group, an amine, and a bromine. Right? So, okay. I know, because we've learned these things, that a hydroxyl group has a higher priority than alkenes, alkynes, alkyl groups, amines, and halogens. So that means I need to number this from left to right to make sure that my hydroxyl group has the lowest possible number. So here I have the terminal alkyne, which is going to get number 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so where's my text box? So I'm looking at a decane, right? 10 carbons in a row. Carbon 1, I'm just going to start typing these out because I can't stay on here forever all night, but 1 YNE because it's got the alkyne. I have 3 all, there's an alcohol at carbon 3. There's a 3 ene also, right, because that's where the double bond starts. I have a 5 amino group because the amine does not have priority over a hydroxyl group. It will be named as a prefix. At carbon 7, I have an isopropyl group. No, I'm sorry, that was at carbon 6, I'm sorry. Can't read my handwriting. At carbon 7, there is a bromo. 8 remarkably has nothing, and carbon 9 has an alkene as well, so we have a diene. Also on carbon 3, the alkene right there, it has some stereochemistry that we need to look at. And so if I look at this group, and this group would have the highest priority using the Kohn-Ingold-Prelog rules. They're on the same side of the molecule, so that would be Z stereochemistry on that alkene right there. So now we just got to put it together. So anything that's a prefix, so 7 bromo, 6 isopropyl, and 5 amino, those are the things that are prefixes that we need to alphabetize at the front of the molecule. It all starts by putting in, the stereochemistry. Can I do that with the, oh cool, I can. So let's see. 5 amino. Ah, I can't type. 7 bromo. 6 isopropyl. And then I have my decane. But I really don't have a decane, right? I have a decene. Now, at this point, it's like, well, which one comes first, the ene or the ine? Enes come before ines. It's an alphabetization issue. So, 3,9 diene. If you wrote down dec 3,9 diene, I wouldn't take off. It technically gets an A there because it sounds weird without it, so they made it have an A in it. 3,9 diene, but I have to cut off that last E and put on the alkyne, but then I have to cut off that last E and put on the alcohol. So, 3Z, 5 amino, 7 bromo, 6 isopropyl, deca, 3,9 diene, 1 ine, 3 all. Just rolls off the tongue, doesn't it? You're funny, Dennis. All right. I'll take one more. One more. And if you guys need me, you can still email me tonight, obviously. I'm getting hungry. I'm eating grapefruit. Hey, you want to see the class? Kenny, you might have been in my class too long if you're saying that. I often say this is why we can't have nice things. You're welcome, Marangeli. I feel like your guys' brains are probably fried by now. It's the end of the semester and it's our last exam. So, I'm watching my clock. Absolutely. Well, it doesn't sound like you guys have any more questions, so I'm going to close. I'm not going to save that. That was a hard naming problem, admittedly, right? That is harder than it should be for anything you'll see in class, but You know, if you look at the back of bottles of stuff, sometimes you'll see names similar to that. I wonder if this has any. I'm sitting at my vanity. A lot of my stuff doesn't have ingredients written on it because I guess it's already on the label. A lot of them have inorganic names too, like pigments and stuff, because all of our stuff's white basically in organic chemistry. If you want the colorful stuff, you have to go to Dr. Ward's class. Okay, Kenny, hurry up. Let me eat my grapefruit, waiting for your question. I just got grapefruit juice all over my dress. Maybe I'll just put that down and wait. I'll have tea instead. If anybody's curious, tonight's flavor of choice is a green strawberry decaf blend. Okay, Kenny, what I'll do then, because I already talked about Markovnikov's rule about 10 minutes ago, so I'm not going to re-answer it because it's just talking about carbocation stability. What I'll say is check in your book, check in your notes, and then rewatch the video at whatever time it was. Who asked the question? Was it Jasmine? Yeah, Jasmine asked that question right there. How we choose carbocation to form Markovnikov stuff. So I went over that in the last probably 15 minutes or so. I used to have a student many years ago who would just call him that Mark guy. And I was like, his name's Markovnikov. That Mark guy. Okay. Last name, not first name, but whatever. If you want really fun organic chemistry names, then you can look up the Chichi-Bobbin reaction and the Noven-Nagel reaction. I'll just leave you with that tonight. Anyway, it's been good. I love you all. I'll see you tomorrow. Email me if you have any questions. I'm going to start preparing for my toxicology class in the morning because I have like 2 classes left in there I need to prepare notes for. So I'll see you guys tomorrow, but email me if you have questions tonight. I should be up until at least 1 o'clock. Twinkie Cam. Twinkie Cam real quick. Twinkie. There he is. Twinkie, are you my angel? So special. Alright. I'll see you guys tomorrow. Bye. Good night.